Okay, hello everyone. Due to the visa issue, Zhengyong cannot be here, so I will give the presentation. My presentation will concern mantle conductivity and tidally induced magnetic field. This talk will be three parts. The preliminary results will include the mantle conductivity and oceanic tidal magnetic field derived from Macau Science Satellite data. MS1 was launched on May 21st this year. Now it is the geomagnetic satellite measuring magnetic field with the highest accuracy in China. So it will provide a very valuable opportunity for probing the mantle conductivity and also the oceanic tidal magnetic fields. It has two satellites. So in this talk, when we say MS1 data, we mean the magnetic field data measured by satellite A. Okay, let's go to the first part, the mantle conductivity. For this purpose, we used 1 month of MS1 vector magnetic field data. And here are the orbits of MS1 satellite and the time series. The workflow to invert the data for mantle conductivity include the following steps. First, we subtract the core and cluster fields, and we also use nighttime data only to obtain the magnetospheric fields. Second, we can estimate the magnetospheric inducing and induced spheric harmonic coefficients. Then we estimate frequency domain Q response, which are sensitive to mantle conductivity profile. And next, we correct for the near surface ocean induction effects using a 3D finite element modeling. And finally, we invert the data for radio conductivity profile using a newly developed inversion algorithm. Here, the magnetospheric field is defined as follows, and only the degree 1 and order 0 term were considered due to the very short data set. And here, the figure shows a comparison of time series of the inducing and the induced coefficients. We found a good agreement between MS1 and swarm coefficients. And using this time series, we can estimate the Q response, which relates the induced coefficients to the inducing coefficients at an angular frequency of omega. And here is a comparison of Q response estimated from MS1 and the swarm data, and also the comparison with published results. And although large error bars were found due to short time data sets, but also a good agreement with published results was obtained. Because the near surface oceans have a very large influence on the response, so to obtain a reliable radio conductivity profile, we need to model and correct the near surface ocean effects. In step 1, we compute Q response in a 3D model with naturally non-uniform oceans, and a 1D model underneath with a finite element solver. And in step 2, we iteratively correct the ocean effects by applying this formula. And after correcting the ocean effects, we use our inversion algorithm to invert the data for mantle conductivity profile. And this figure is the comparison of observed response and predicted response. Also, we got a good fit between these two responses, and it indicates that our inversion fit the data, and it is reliable. And here, this picture shows the recovered mantle conductivity obtained with 1 month of MS1 data. We also compare our result with two published results, and we found that 90% credible interval estimated by only 1 month of MS1 data covers the two published results. And note that they used more than 6 years of data. So since we will have more MS1 data, so we can improve the result and in the future. Okay, let's go to the second part, the oceanic tidal magnetic field. The workflow to extract the M2 tidal singles is similar to that used in mantle conductivity imaging. And in step 1, we subtract core, crust, and magnetospheric fields. And we also use only nighttime data. Then we can estimate, we express the magnetic field potential as follows. And we can use this model to fit the residual field, and we can obtain the coefficients. Then we can the tidally magnetic field at any location R and an angular frequency can be computed as follows. And I will also develop a new finite element for the solver to compute the predicted tidally magnetic field for a given 3D model. And here we compare our modeling results with those obtained by a spherical harmonic finite element method and those of integral equation method. This we can see that a good agreement among these results, and it validates the algorithm of our for modeling. Here we try to recover the tidally induced magnetic field, use 8 years of storm data, and here the top one is the result calculated by forward modeling, and the lower one are the magnetic field extracted from 8 years of storm data. Yeah, this picture are green well. And we also try to add 1 month of MS1 data to the storm satellite data, and we got a very similar result. But we also found that there is no chance to recover tidal magnetic fields from only 1 month of either MS1 or storm satellite data. So more data are needed. Okay, in conclusions, we have successfully developed a new 3D finite element solver. It can compute the induced magnetic field caused by a variety of sources. And we found that calibrated MS1 data allows for obtaining trustworthy Q response, and so we can constrain the mantle conductivity. But for the tidally magnetic field, we need more MS1 data. So thanks for your attention.